This is the video for section 8.5. We talk about the binomial theorem. So, a lot of, did I go too far? There we go. A lot of what we know about mathematics comes from patterns and things. And so Pascal's triangle is this really cool thing that has so many patterns in it. People have studied and found all kinds of things in Pascal's triangle. And it's named after Blaise Pascal, and he wrote whole books on it. And this is what it looks like. Okay, you may or may not have seen it before. And it keeps going each row. I mean, there are more. You can do as many rows as you want. So it came about because of gambling. A French nobleman had approached Pascal with a question about gambling with dice. In fact, I think it had something to do with they were in the middle of a game and they had to end, and they couldn't decide who would get the pot, and they were going to give it who had the best chance of winning, and so they were trying to figure out who had the best chance of winning. That was the problem, I believe, as I recall. So he talked to another mathematician whose name was Fermat, and what they came up with was this triangle that helped them to solve that. And this is it. So I'm just going to show you a bunch of different things that come up with this triangle. This was a study, and they were looking at the number of ways to get a given sum when you throw n number of dice, right? So if you look here, there's the 1, there's the 1, there's 1, 1, there's 1, 1, 1, 2, 1, and you see that it's the triangle. He's got it organized a little bit differently, but it is the triangle. And so look at how we build it. You notice that the outside edge of this triangle are all ones. It starts with a single 1, and then all the edges are 1s. And then each number is the 2 numbers above it added together. So by above, you mean like touching on this. So like this one and this one, right? So here's how it fills in. Let's see it again. There's the 1, there's the 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. And we got 6. Then we got 4. So take a minute and fill in what that last row would be. See if you can figure out the next row. All right, hopefully you got, this would be a 1, right? So this is going to be 4 plus 1, so it would be 5. 4 plus 6, that would be 10. And this was another 6 plus 4, so that would be 10. And then this is 4 plus 1, so that would be 5. And then a 1 on the outside. So that's how we would do it. So the next row would go 1, 6, 15, 20, so on. So what we find all kinds of things with Pascal's triangle. So if you just take the diagonals, looking right down the, these are all 1s. Well, I think I have these marked. The next one, if you see all the gold ones there, those are the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, right? The next one are what we call triangular numbers. I'll show you in a second what that is. The next one turns out to be tetrahedral numbers, right? And I don't know, there could be more than that. So triangular numbers are the number of dots it would take to make a triangle, and they're offset, right? So 3 is one of our triangular numbers. Well, 1 is included in that, but so this would be 1, 2, 3, 4, 5, 6. No, 6 dots can form this triangle, right? And this one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots would form a triangle. Goes over at 15 dots, right? So you notice that like 4 dots would not form a triangle. There's no way to get 4 dots in a pattern like this to form a triangle. Tetrahedral numbers are like a 3-dimensional thing. Same kind of idea, but you see that you have the 1 on top, and then you have 4 below it. Actually, it's probably 3, 4 making the top, so that would be 4. And then you would have, I don't know what the next one is. 10? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's 10. I don't remember tetrahedral numbers. So numerous people have found it. You notice that if you take Pascal's triangle and color all the numbers certain ways, you get all kinds of patterns. So like here, this one, if you color just the evens and the odds, you get this thing that, I don't know if any of you have seen this before, but this looks like the pattern of the Sierpinski triangle, which is a fractal, which people are just now studying, and there it is in Pascal's triangle. It's totally amazing. If you look about the rows and you add up the numbers, we get 1, that's 2 to the 0, 2, 4, 8. You see that these are all the powers of 2. This one even goes down to this 9th row, or actually it's the 10th row, but it would be 2 to the 9th. So oftentimes you notice this 0 up here, that first one, that just with that number 1, often turns out to be kind of called the 0 row, and we'll run into that again in a minute. Okay, so then there's the shallow diagonal. So we talked about the diagonals that go, that would go this way, but if we actually were taking them kind of more shallowly, right? We're taking from one end of one row to the beginning of the next row. You draw a line, and then you add up those numbers that it touches, the line goes through. We get, anyone recognize this? 1, 1, 2, 3, 5, 8, 13. We talked about this in 8.1. This is the Fibonacci sequence. So amazing. Fibonacci sequence is in there too. So we can also see like powers of 11. Well, 11 to the 0 power is 1. 11 to the first power is 1, 1, 11. 11 squared is 121. So it works really great until we get to row 5. Then we have 2-digit numbers, so you have to carry them. But it still works. If you think about when you carry the 10, you'd have 0, carry the 1, so you'd be 10 plus 1 is 11, carry the 1, and 5 plus 1 is 6, and so on. But they're in there. Those powers of 11 are in them. So now we get to what we are going to talk about today. And this we will use the Pascal's triangle for as well. So when we have a binomial, so a binomial is anything with 2 parts. And a binomial is technically a polynomial, but what we're going to talk about today could be used for things that aren't technically polynomials. They can have square roots, or they could have variables in the denominator, whatever. It's just 2 terms, okay? And then it's raised to a power. Now, so this is raised to the 5th power. So I don't know about you, I really would not want to multiply this all out. I would have to first we would do this, And then I'd get this trinomial, and I'd have to do this. And then, so then I'd have, I'm not sure how big, maybe 4 parts. And then I'd have to do it to this one. And then I'd have to do that answer to this one. And then I'm getting something really big. In fact, it would have 6 terms even when I've simplified it. So we really want to find a good way to expand a binomial. And by expand, we mean instead of having it in this factored form, we want to have it all multiplied out, no parentheses, just all multiplied out, right? That would be what we would be calling expanding. So let's look at the pattern, okay? We'll just look at these first 5 so that we can see what that pattern is. So look at that first one. So x plus y to the 0 power. So anything to the 0 power is 1. So that one is a 1. All right, so x plus 1 to the 1 power, well, that's just x plus 1. Right. Those were easy so far, right? Okay, x plus y squared. So when we square it, we have to multiply it out. And remember, we end up, the 2 middle terms are alike. And so we get this 2xy, right? So you notice the coefficients. That would be the first pattern we're going to look at. And is anyone recognizing that yet? Okay, to find x plus y cubed, we would take this and multiply it by x plus y. And that gives us this. All right, so are you seeing the pattern? Look at the coefficients. These numbers I have in color. What do you think the coefficients for the 4th one will be? I hope that you're thinking about that Pascal's triangle. You notice that so far, these coefficients are the numbers in the triangle. So this one should be a 1, a 4, a 6, a 4, and a 1, right? And sure enough, that's what it is. And then we would have to do this one. Okay, so this has 5 terms, and we're going to multiply it by x plus y one more time to get the 5th one. I did all that work for you, so you didn't have to. Let me erase some of this so we can look at these patterns. Okay, so first of all, the numbers. The numbers are certainly the very same numbers that were in that Pascal's triangle. Now, in Pascal's triangle, so when n is 5, technically we're not using the 5th row. We're using the 1, 2, 3, 4, 5, 6th row. But if we consider that the first row is the 0 row, then we can talk about it being the 5th row, right? It's the one with a 5 on the counting number, diagonal. So that matches. It's the one that if we start the row counting by 0, this turns out to be the 5th one, right? What else? What other patterns do you see? I wish that you were here so we could talk about it, because I'll bet you see some other patterns. Let's look at the exponents. Okay, so let's look at the degree of each term. Okay, so in this first one, well, the degree of the first one is just 0 degree, right? There's no variable. So this has a degree of 1, and this has a degree of 1. And it was to the 1st power. And look, this has a degree of 2. And how do we figure degree when it's 2 variables? We add them up. So I have a 1 and a 1. So that's degree 2. And that's degree 2. And that was to the 2nd power, right? So in this third one, when we take it to the third power, all these degrees should be adding up to 3, right? So I have 3, I have 2 and 1, that would be 3. I have 1 and 2, that would be 3. I have y cubed, so that would be 3. And that is going to be true in every one. So look on this fourth row, we have a 4, we have a 3 and a 1, we have a 2 and a 2, we have a 1 and a 3, and we have a 4. Every single term has the same degree as that power that we started with. And the same thing happens with 5. Now, let's look at what happens to those degrees. Okay, so let's look at the pattern for the degrees. So let's first look at the x terms. So you can't see much pattern in the first one or the second one because there's only one x in the whole thing, right? But here, let's look, we have the x exponent is 2 and then 1. And in the third row, it's 3 and then 2 and then 1. And in the fourth row, it's 4 and then 3 and then 2 and then 1. So you got the idea? The first one is going to start with whatever degree it is, the n that we're talking about here, right? And it starts with that one, goes x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1. If you wanted to think about an x being in the last term, we could certainly think about it being x to the 0. And then that would take us all the way down, 5, 4, 3, 2, 1, 0, right? And now switch that around and look at the y's. There isn't a y in the first one, but we could consider it y to the 0. Maybe I should change color for the y, so we're looking at the different numbers. So that'd be 0, and then we have 1, and then we have 2, and 3, and 4, and 5. And so the first term in our binomial starts at the full n degrees, right? And goes down 1 every term. While as the second term starts at 0 degrees, right? So it's not even there in the first one, but then it goes up until it gets to n. So that by the end, the second one is up to the full n degrees. At the beginning, the first one is at the full n degrees. Okay, so, and there's our row we used, right? So if we wanted to do something in the 6th power, I would use this row, right? If I wanted to do something in the 7th power, I would use this row. Okay, so here we go. The Pascal's triangle will be in row n plus 1 because the first one was a 0. Right, so if we're counting the rows, there are n plus 1 of them to get to the one we want. The total degree for each term was going to be n, the same as we started with, and the exponents on the first term begin at n and go down to 0, and the exponents on the second term begin at 0 and go up to n. And there are always n plus 1 terms total because, think about it, we have all n plus we have the 0 degree one. Okay, so here we go. We're going to do this one. So the 5th row, so let's see, our 5th row, and you have a triangle in front of you. I don't. But I'm going to just write them up here, right? That we have 1, 5, and then 10, and 10, and then 5, and 1. And you would know if you have them all, because you should have one more than whatever number you're doing. So we're doing 5, so I should have 6 numbers, right? Okay, so the first one will be a 1. And then my first term, x, will be to the 5th power, and my second term will be to the 0 power. Okay, so now I'm going to do 5. So there's my coefficient from here. And then I'll have x to the 4th. And my second term, which is the whole 3y, right, to the 1. So even though it's not just a variable, it's the whole 3y that's there. Those are my two terms, x and 3y. Sorry, that's a 1, not a 7. Plus, then we have a 10. And my x now is to the 3rd, because I'm going down. And my 3y is to the 2nd. I can always double check because they have to add up to be 5, right? And then I have another 10, x squared, 3y to the 3rd, plus, I know I was writing too big, but I can't write small with this stylus. 5, and then I'm up to x to the 1, and 3y to the 4th, plus 1 x. Oh, x is to the 0, so let me just erase that because I don't need to put it in there. So x is gone, and I have 3y to the 5th. If it helps you to write x to 0, that's fine, because the second time through, we're going to simplify, and so we could catch those sorts of things when we simplify. All right, so we're going to start with x to the 5th. Okay, so now our coefficient has got to be combined with this number and this number. All right, so this is 5 times 3 to the 1. So 5 times 3, that's going to be 15. X to the 4th, and then y to the 1. Okay, plus, okay, so this time I've got 3 squared, so that's going to be 9 times 10, so that's going to be 90. X to the 3rd, y squared. So the numbers in the next one, now I have 3 cubed, so that's 27 times 10, so that's going to be 270, x squared, y cubed, plus, now I got 3 to the 4th, so let's see, 3 squared is 9, 9 squared is 81, so that's 81 times 5, which I don't know. 81 times 5 is 405. And then I have x, y to the 4th. Ooh, I can almost do it. And 3 to the 5th is 243. Oh dear, I'm almost going to make it. Y to the 5th. Ha, I did it in one row. Okay, so let's just go back over this a little bit. So here are my numbers. So even though I had coefficients of 1, 5, 10, 10, 5, and 1, I had a number inside here, so that has to be included, right? So I have 1, 15, 90, 270, 405, 243. But I do have all of my exponents are going to add to 5 still, right? So I got 4 and a 1, I got a 3 and a 2, I got a 2 and a 3, and I got a 1 and a 4, and then the 5. Okay, let's try this one. So this time we're only going to the 4th power. So on our triangle, I believe we have 1, what is it? 1, 4, 6, 4, 1. Okay. So this time our first term is 2p and our second term is going to be negative 1. Okay. So we're going to use this negative 1. It's kind of like it's 2p plus negative 1, right? All right. So we've got 1. That's always our first one. 1 times 2p to the 4th times negative 1. Oops, that's to the 0. I don't need to write. I'll just write 0. Plus, the next one is a 4. 2p to the 3rd, negative 1 to the 1. Plus 6 2p to the 2nd and negative 1 to the 2nd, plus 4 2p to the 1st and negative 1 to the 3rd. I still ran out of room, plus 1. 2p is to the 0. Well, I'll just write it. And then negative 1 to the 4th. Okay, so as we simplify here, we do have other numbers, so we have to keep track of that 2 that's being taken to a power, right? I gotta change to a different color so I can keep track of what I'm doing. All right, so I've got a 1 and a 2 to the 4th. So that 2 to the 4th is 16. And this negative 1 is to the 0 power. So that's going to be a plus, right? That's going to be a plus 1. And then I have p to the 4th. Okay, so this time I only have one actual variable. And so when I'm looking at the powers that match, it's with that negative 1, right? So it's 3 and a 1, but we're not going to see that in our final answer. Okay, plus. Now, I've got 2 cubed is 8 times 4 times negative 1, right? So that's going to be negative 32p cubed, because the negative 1 was to an odd number, plus, okay, so this time I have 2 squared, so that's a 4, times my 6, and negative 1 squared is positive 1, so that'll be positive, so I got 24p squared. So this time I will have a negative, because it's negative 1 to the 3rd power, so it's going to be negative. I got 2 to the 1st power, so it's just 2 times 4. And then I have p to the 1st. And in this last one, this whole thing is a 0 power, so that's a 1. And negative 1 to the 4th power is a 1. So that's going to be plus 1. So some of the things you can double check as you look. When I have this negative to one of the powers, it really does alternate signs, right? So I got plus, minus, plus, minus, plus. And you notice that this one I had already written the plus sign. So I just left it. I could erase it if I wanted to and put just a subtract, but it doesn't matter which way you do it. Okay? All right, so, t plus 4 to the 40th. Nobody wants to do 40 rows. First of all, by the time we get to 40 rows, we have 41 terms on that row in the triangle. And so we don't want to do it that way, right? So this would not be a great problem, and I promise I won't ask you to expand something that is that big. But I might ask you for certain information about that expansion. So you could tell me any term that you wanted to, and we wouldn't have to do the whole thing. So let's look at what that would look like. It turns out that whenever we are, so those numbers in the triangle, which came, remember, from the dice and the different ways of getting something, it turns out that they are it's called a binomial coefficient, and it's like the combination. So some of you may have heard of a combination, right? We often read this. Now this is not a fraction. This is not a fraction. There's no fraction sign. It's in parentheses, and it's one number above the other, and we read it and choose R. Okay? And here's how we do it, and this comes from our probability or our number counting theory, and it's the number of ways that you can choose n things take an R at a time. So, for example, if I had 3 things, but I only wanted to choose 2 of them, the number of different ways that I could choose 2 of them out of 3 things would be 3 choose R, or 3 choose 2. So that would be 3 and 2, right? And here's how it works. N factorial, remember we talked about the factorials, so that's just the n, the number up here. And we have that number on the bottom, the R factorial, and then we have the difference between them on the bottom too. So there are ways to remember that, but I'm not going to go into it right now. You may or may not be familiar with it, and you can write this formula down. So I'm not going to worry about telling you how it comes about this time. But this is an important formula. So you'll want to have that. And here's some practice. Okay? So these are called the binomial coefficients, and they are the coefficients for this 5th degree. Okay? So you notice that the n up here, that is the top number. That is the same as this n. And it will always be that way. And then the bottom is going to go starting with 0 up to 5. So the bottom number is the exponent on the second term, right? When it started at 0, and then it went to 1, and then it went up to 2. And so let's look at what we get here. We get n factorial, so that would be 5 factorial over 0 factorial times 5 minus 0, which is 5 factorial, which is 1. Okay? So this one would be 5 factorial over 1 factorial, and 5 minus 1 would be 4 factorial. And remember how we talked about simplifying. This is 5 times 4 factorial. Those would cancel, and you would be just left with 5. All right, so this would be 5 factorial over 2 factorial, times 5 minus 2, which is 3 factorial. All right, so this is 5 times 4 times 3 factorial, so those cancel. And 2 factorial is just 2 times 1, so the 2 I could take out of here, and I end up with 10. Okay, so you notice on this one, something interesting happens. The bottom numbers are just switched, but they're the same, right? So this is going to turn out to be 10. And 5 factorial over 4 factorial, and then 5 minus 4 is 1 factorial. And if you notice, that's the same as this one, so that's just going to turn out to be 5. And 5 factorial over 5 factorial times 0 factorial, and that turns out to be 1. And you also notice here in this formula, it's really important for us to have a 0 factorial, first of all. It works in everything else, and we want it to work in the one where you get a 0. But what do you notice about these numbers? That's the row. That's the row on Pascal's triangle, right? So this is that row. That's the one we just figured out. And every row can be determined by a combination. So that means that if I want to take something to the 40th power, I don't have to do all 39 rows before it. I don't have to figure them all out, so I can figure out that 40th row. I can actually do it in a given, just one spot, whichever spot I wanted to come up with. Okay, so here's the binomial theorem. This is what it looks like. So any expansion, so we're looking any expansion to the nth power, right? So you notice that every coefficient then has a combination, right? The n choose something, right? So n choose 0, n choose 1, n choose 2, and so on, all the way up until we get to n choose n. Just like we just figured out with the 5s. And then the terms, the a starts at the nth degree, b starts at 0 degree, right? And a goes down and b goes up. And here is a way to write it, I think in summation form. Okay, so here we notice again that r is going to start with 0, right? So b is to the 0 power in the first term, right? And then we subtract them, that would still just be n minus 0. So in the first term, it's going to be 0. So you notice it's important for this summation to start at 0. And it goes up to n, which gives us n plus 1 terms, right, that we're doing. And you notice that if I take n minus r plus r, I get n, right? So my exponents have to add up to be n. And this term right here, this is the same as the power of the second term. All right, so let's see how that would work. So we're going to use this one. We're going to do this one to expand, even though we could easily come up with the 4th row. We're going to do it with the binomial expansion. So, all right, so the first coefficient is 4 choose 0, and then I have 2x to the 4th and negative 3 to the 0, plus 4 choose 1, 2x to the 3rd, negative 3 to the 1, plus 4 choose 2, 2x to the 2nd, negative 3 to the 2nd, plus 4 choose 3, 2x to the first, negative 3 to the third, plus 4 choose 4, 2x to the 0, negative 3 to the fourth. Okay. So now when I'm looking here, of course it's to the 0 power, that's going to be gone. And now I need to figure out this 4 choose 0. Anytime you have a 0 in there, the answer is always going to be 1. There's only one way to choose nothing, and that's to choose nothing, right? So you can plug it into the formula if you want, but anytime it's 4 choose 0, or any number choose 0, it's going to be a 1. So this is a 1, and then I have 2 to the fourth power. So I've got 16x to the fourth. Okay, so let me also I was going to see if I could do, so on your calculators, you can find this combination. You don't have to, you don't have to figure out that formula every time. It's actually in your calculator. And so what you want to do is put in the first number. So you put in the n, so I'm going to enter 4. I already know this is going to turn out to be 4, but I enter 4, and then I go up to math, and I go over to probability, and the very first ones are NPR and NCR. I want the NCR. I choose that, and then I put in the other number, 1, and enter, and that gave me a 4, right? So this one was 4. When I put in N choose 2, so I would put in 4, go to the math, go over to probability, it's on the end, go down to number 3, which is NCR, and then I put in 2, enter, and that gives me the 6. So try putting try putting the next one into your calculator. And 4 choose 3. Okay, you should come out with a 4, but try that and see if you can do it. All right, so in this one I got 2 cubed is 8 times 4 is 32. Uh-oh, see, I was multiplying up, I might as well. I might just as well not try to multiply some of them together and not others. So I'm going to have 4 times 8, and then 3 to the first power will be negative 3, and then I have x cubed. Okay, so that's going to be 8 times 12, so I got negative 8 times 12 is 96x cubed. Okay, so then the next one will be 6 times 2 squared, that's going to be 4, and negative 3 squared is going to be 9, and then I had my x squared. So that is going to be 9 times, well, let's just do 6 times 4 times 9 is 216. And that was positive because the negative 3 was to an even number, right? And these, of course, match up with the other one, 4 and 3. That's going to be a 4, and that's going to be a 1, right? So I have 4 times, this is 2 to the first power, and this is negative 3 cubed will be negative 27, and then x to the first power. So that's going to be 27 times 8 There's another 216. This time it's negative. And then plus this last one, that's a 1. This 4 choose 4 is a 1. And so I just have negative 3 to the 4th power, which is going to be positive 81. So here is my expansion. Okay, so for any given term, this is kind of what we're looking at. And this is the same thing that was in that summation thing we looked at. So if we get up big numbers like to the 15, we don't want to do them all. I don't want to do them all, right? So I want to find the term here that is x to the 9th, y to the 6th. And sure enough, 9 plus 6 adds up to 15. So there will be one, right? So that means that I have this number, this combination here, right? And then I have 2x to some power, and I have 3 to some power. Wow. They didn't put a y in here. I think they meant to have a y here. All right, this one's going to be a 6. This one's going to be a 9. So that means that, remember that the r is the r is the same as this. So that's a 6. And the top, the n, is the same as the total. So that's a 15. And so this is going to give us the term we want. All right, so in your calculator, go to your calculator now and see if you can put in 15 choose 6. And hopefully you did that and you got 5,005. Okay, times, now this is going to be 2 to the 9th times x to the 9th. So I go 2 to the 9th. Well, that's going to be 512 x to the 9th. And then we have 3 to the 6th. That is going to be 729. So huge numbers. But let's just see if we can. 5,005 times 512 times 729. Okay, so that is 1,868,106,240x to the 9th. And that is our term. Yeah, if we'd had a y in there, which makes this thing, typically you have one there, but that would have been on there too. Okay, here's one more for you to try. So see if you can do this one. Do it the very same as we did the last one. Get the term that has this. Okay. Okay, hopefully you got it. Remember that we're going to do the combination of 16 things taken 12 at a time. And then this first one is going to be 3u to the 4th power and z to the 12th power. Yes, they add up to 16, so that's good. All right, so 16 choose 12. Let's go to your calculator. Hopefully you did that, and I should have had it done so that I could have been all ready for you to be done. 16 choose 12 is going to be 1820. 3 to the 4th is 81. U to the 4th, z to the 12th. And so then 1820 times 81, is going to be 147,420, u to the 4th, z to the 12th. So these sorts of problems where you're just finding the one problem, this is very typical for what you might find on the final. This is very normal for them to ask a question like this. You don't have to figure out all the terms, just the one that they ask you for. Okay? All right, so here's one more. I want you to pause the video and try to do this whole thing yourself and see if you can do it. We're only looking for this one term that has those variables in it. Okay, I hope you did it. It's 22, choose 3, right? Because that's our 3 there. And then it will be y to the 19th and negative 2q to the 3rd. So 22, choose 3. Is 1540 and y to the 19th. And then I have negative 2 cubed and q cubed. So negative 2 cubed is an odd exponent, so that's going to be negative 8. So I want to do 1540 times negative 8. That's going to be negative 12320. So 12,320 y to the 19th q cubed. Okay. All right, just so you can get a little chuckle. Here is the incorrect way to expand a binomial. So, if you expand the binomial this way, you're not going to get credit. But it is an interest. That is not what it means. But it does mean that technically, doesn't it? But that is not what we're talking about. So, please don't. I hope that you can practice these. I didn't even give you any practice problems. So, do the homework and we'll talk about this in class.